we've messed with power series and with the Taylor-Maclaurin series, and one of the things that's actually really useful with them isn't just the calculus of them, which is useful, no doubt, but it's the idea that you can substitute in, right? So if I have a function that is identical to some sort of power series here, then instead of x, if I want to plug in something else, I just plug it into the function. I mean, that's how functions work, right? I replace everywhere I see an x, I replace it with y. Okay, what does that mean? Well, e to the x has a very well-known Taylor series or Maclaurin series. N equals 0 to infinity, 1 over n factorial x to the n. Hopefully you can do that. Hopefully you feel good enough about the techniques that you could generate this. It's probably the easiest Maclaurin series to generate. But if I want to set e to the 2x, now you could generate a Maclaurin series the old-fashioned way. You could take f prime, f double prime, and you could try to find out the pattern, and you could try to figure out what that Maclaurin series looks like. But instead, why don't we use this? You say, okay, well, if e to the x is this, e to the 2x, I just replace x with 2x. And now I can distribute the exponent, and I get 2 to the n times x to the n. So I bring out that 2 to the n, and I now have a power series. So in seconds, I can generate a Taylor series for a different function, but it's related. It has the same kind of parent behavior. It's one of the reasons we like to learn families of functions, because we find that they have very similar characteristics. But you can do even more complicated things than just e to the x or e to the 2x. What if I did like e to the negative x squared? The so-called error function that, well, when you integrate it, you get what's called the error function. And this has no known closed form of an antiderivative. So if you try to take the integral of this, you'd have a lot of issues. You'd be stuck, and you could try everything in the world, but you're not really going to get there. But so what we can do is we can say, okay, well, I know what e to the x looks like. So instead of x, I'm going to replace it with negative x squared. And so then I get a negative 1 to the n, and then I get x to the 2n. Okay, well, why is that useful? Well, now that I have this, I can take the antiderivative of that. I can easily just take an antiderivative. I get another polynomial, and it's not a closed form, it's still an infinite series, but it's better than what I had. So there's a lot of power here, no pun intended, and the whole point of this is leveraging known power series or known Taylor series and just plugging in an additional value. So this always goes back to the old adage, never work harder than you have to.